Alright, so to begin a noise parameter measurement, you need to start by calibrating all the losses in the system with the vector network analyzer. In this picture we have the VNA overhead. It needs to be a 2-port network analyzer. Step 1 involves measuring everything in the noise path. So the noise path is defined by anything between the noise source and the device under test that you want to measure. So here there's a label on this port for the device under test, or DUT, and then here is where the noise source will eventually be attached to. So we need to characterize the circuit performance between those two. During this test, the impedance generator needs to be set in state A, which is a through state. So it internally switches the RF path from one port to the next. And that concludes step 1. So the next step that you need to perform is measuring the S1P reflection coefficient of your noise source. So in this picture we have the noise source here. It's not powered, so this is the cold measurement. So you just connect it, measure the S1P, and save the results. That's it. So next step is very similar to the previous step. You measure the reflection coefficient of the noise source again, but this time with the power 28 volts applied to the DC input. And that can be seen over here where the 28 volts is turned on. And that's it for step 3. So the next step has a little bit more going on. We need to now include our spectrum analyzer or noise figure analyzer, whatever is going to be used to measure noise power in the setup. So here we have a BNC 1365, I think. You might need to edit that if I got it wrong. I can't read it. So here we have a preamplifier, two preamplifiers in fact. They're both low noise wideband amplifiers, and they're just used to undermine the noise figure of the spectrum analyzer. So the spectrum analyzer, some general considerations is you need to figure out all the front-end attenuation ahead of time. So here we've set the RF attenuation to 0 dB, and it has an internal preamp. You want to enable the internal preamp. And then on top of that, you need to add some external preamps, which are shown over here. Then you want to hook it up to one of the ports on your VNA and measure a reflection coefficient at the end of that cable. So that cable is eventually going to end up at the output of your DUT. But for now, the purpose of this is just to de-embed the reflection coefficient of the entire system downstream of that point. So an additional consideration for step 4 is VNA power as seen by the preamplifier. So the VNA is actually sending a signal out here and measuring what gets reflected. If that power is too high, you can saturate the first amplifier or possibly the second amplifier or anything in the chain downstream. Generally, you want to make sure that your P1 dB is you're not measuring anywhere near your P1 dB. So your input P1 dB, let's say, is minus 10 dBm. You want to measure at least 10 dB below that as when configuring the power on your VNA. So the lower the power, the better. The only thing you want to consider when lowering the power is that you'll increase the uncertainty on your VNA power measurements. So you might want to reduce your IF bandwidth to maybe 1 kilohertz. Depending on the speed of your VNA, that will slow it down quite a bit because it's averaging more noise out of your measurements. The next step involves measuring the reflection coefficients of the impedance generator. So now the noise source is connected to the noise source port of the impedance generator, and the power is turned off. That's step 5. And we're going to measure on port 2 of the VNA the reflection coefficients of the 4 states generated by the impedance generator. So there's state A, B, C, and D. They each have their own separate commands, and we need to measure the reflection coefficients of all of them before we move on. Step 6 is exactly the same, except you need to configure the impedance generator into state A, which is again the through state, and turn the noise source power on and measure the reflection coefficient in the on hot state. and that's all. And that's everything for steps 5 and 6. So the next two steps, steps 7 and 8, we now connect the receiver or the spectrum analyzer with the preamps to the DUT connector of the impedance generator with the noise source also connected. At this point, we're done with reflection coefficient measurements, so you can power the VNA down. It's actually recommended that it gets powered down or the port powers get turned off, because it can sweep power, and the power is quite high. And now that we're measuring noise power, the noise power is quite low, and it could actually present itself as interference to your noise measurements, which could reduce your accuracy. So this is the first noise measurement being done. What you're going to do is start off with the noise source off, collect several averages on the spectrum analyzer, and save the power trace. And then steps 8 is when you turn the noise source on, you should observe a small or moderate increase in the noise floor as seen by the spectrum analyzer, depending on which noise source you're using. If the noise figure of your preamp is 5 dB and your ENR is 15 dB, you might expect it to increase by the difference between the two approximately, just to make sure everything's connected correctly. And once those are collected for both the hot and cold states in state A, you can switch the noise source off completely and switch the impedance generators to B, C, and D and collect the noise spectrums for those different states. And then you're complete. And then you're done with this step. So before we move on to the next step, all the steps that have built up to this have been for the purpose of calibrating the noise of our measurement equipment itself. So now we're ready to add a device under test. So the first thing you want to do, step 9, is measure the 2-port S parameters of your device under test. The picture here does not show it connected, but you would power up your VNA again, calibrate it, measure your S parameters of the device under test, or your amplifier or low noise amplifier, and then reinsert it into the spectrum analyzer setup below, between the impedance generator and the spectrum analyzer. And then you can leave the noise source off for the remainder of the tests. There will be cold noise measurements, and you need to change the impedance generators between states A, B, C, and D, each time collecting a well-averaged trace on the spectrum analyzer. And after that, we can compute the noise parameters of the device under test by running them through the noise parameter solution script. So while measuring the DUT in steps 9 through 11, power becomes power in the VNA measurements can be a serious consideration. If you have a lot of gain in your amplifier, you don't want to overdrive the VNA port or the spectrum analyzer for that matter. So you need to make sure that your VNA port powers are well below their P1 dB by, again, 10 dB. Also, the spectrum analyzer, when you hook the DUT back up to the spectrum analyzer network, in our case, we generally recommend high sensitivity, but when you do that, you reduce the linearity of the spectrum analyzer, and it may be necessary to validate your setup. So if your spectrum analyzer starts showing you warnings like ADC over voltage or input power exceeded, you're probably going to want to turn attenuation back on, raise your reference level, maybe turn your preamplifier off. That will require recalibrations of steps 1 through 8, but if you consider it ahead of time, you won't have to redo it. So perhaps it's something you don't find out until you actually add the device under test into your setup. So maybe we should include this in some of the earlier steps. You need to consider your setup before you start the test, how much gain you have in your setup, and what you're actually trying to measure. So if you have a 40 dB amplifier, you should know that ahead of time so that you don't add too much preamplification to the spectrum analyzer and overdrive it. It'll become nonlinear, and once it's nonlinear, you can't measure noise parameters accurately or repeatably. So when you complete steps 1 through 11, you should have a set of files that look similar to this. If they're in exactly the same format, you can run the noise parameter solution script directly on these files. The structure of the files is p_anything is power measurements. So this is the power measure, the spectrum analyzer measurement you collected from the device under test on the spectrum analyzer. Well, the impedance generator is in state A when the noise source is off, and this for when the noise source is on. This is state B, C, and D, which is only done when it's cold. And then this p_rec is part of the receiver calibration. So this is when the DUT is not in the system. Again, it's going to be hot, cold, and then cold for B, C, and D. And inside these files, they are pretty simple. They're just their frequency followed by power and dBm. So most spectrum analyzers will have an output similar to this. Often there's a header. It's either has a hashtag or a exclamation mark. That can all be ignored. All you need is this. Once you import that, the script knows how to read that in. The other two file formats are S2P files and S1P files. So these are our VNA measurements. So S1P file are purely reflection coefficient measurements. So they're one-port measurements, hence the 1P. Inside of them, very similar. They have a frequency. They have a, in this case, real imaginary format. So this is the real component of the reflection coefficient. This is the imaginary component of the reflection coefficient. Often this can be in dB angles or other formats as well. Generally, our script is readily available to handle most touchstone file formats, but in this case we have real imaginary. The other format is S2P file. So this is the DUT, for example. The DUT is usually an amplifier, a two-port device, and since it has two-port device, it has a lot more information in it. The header usually gives you an indicator of the format, so S11 should be the input. Technically, you could measure the S parameters backwards, so if you install the amplifier backwards, so that port 1 is the output, port 2 is the input, we'll have trouble, the script won't work because the gain is very directional. You won't get gain going if you plug it in backwards, essentially. So the port 1 is generally the input to the device under test, S22 is the output of the device under test. And the order it goes real imaginary of S11, real imaginary of S21, real imaginary of S12, and real imaginary of S22. As long as it follows that format, that's the standard touchstone format. And then that's pretty much it. So as long as there's one of these files or equivalent, you can use it. In the solving noise parameter script, if you choose to deviate with your file names, you just have to make sure that you adjust the first few lines of the script. This is an example, but eventually we'll have a graphical user interface. You can type whatever file name you want in. You just have to put it in the appropriate spot. Just try opening this up just to show you what I mean. Might actually be easier. Notepad++. So you just have to change these file names. They're the first few lines. Once this is just input file reading, there's a little header here, and then everything else doesn't matter. So there's no more file reading till the bottom of the file. So the absolute reflection coefficient is actually in linear scale. 0.1 corresponds to 20 dB return loss in the power domain, and then 0.2 would correspond to minus 14 dB reflection coefficient in log domain. So generally speaking, anything less than minus 10 S11 is going to be well matched. So this is a broadband well matched amplifier, and the noise performance is also well matched in this case. But that's not the not generally true. You can have a well matched amplifier and have the optimal noise impedance to be completely somewhere else on the Smith chart. It just happens to be designed that way with these broadband mini circuits amplifiers.
In addition to the raw measurement data for the mini-circuits low current amplifier that we collected with the BNC 1365 spectrum analyzer and the Copper Mountain VNA, now let's break down the data and results using the following 6 figures. The first figure is NF-min. This plot contains the minimum noise figure. This noise parameter describes the minimum noise figure achievable for a device under test. The next image is RN-DUT. This plot contains the noise resistance in ohms. This noise parameter describes the noise sensitivity to mismatch from the optimal noise impedance, also known as the admittance reflection coefficient. The next image is NDUT. This plot contains the invariant noise parameter. The noise parameter is similar to the noise resistance in that it describes the mismatch from the optimal noise impedance. However, this noise parameter can change depending on the real part of the optimal impedance. Next, we have ABS gamma opt. This plot contains the magnitude of the optimal reflection coefficient. The noise parameter gamma opt describes the optimal signal source reflection coefficient that will produce minimum noise for a given device under test. Now we move to the phase gamma opt. This plot contains the phase of the optimal reflection coefficient. The noise parameter gamma opt describes the optimal signal source reflection coefficient that will produce a minimum noise, again, for a given device under test. And finally, we look at gamma opt. This plot contains the optimal reflection coefficient, gamma opt, on a Smith chart. Although frequency values cannot be seen, the chart is useful for visualization.